Hello everyone, welcome. I think there might be one or two more people coming in, but I think we're going to get started. I hope nobody objects, but we are going to be recording today's presentation so that those who don't live in the area are able to see it. We got some requests after our last talk, and we hope that our recording goes well. I'll start by saying welcome and thank you all for being here. I'm Alex Stauffer. I am Vice President of the Historical Society. Just a show of hands, how many people came to this event in March? Okay, we have a couple. Okay. How many tried to come? Okay. We're happy that you were able to be with us this time. We're really excited to present again the history of the dinosaur tracks discovery right outside of Coopersburg in Upper Saucon Township and their theft, and then a deep dive into the geology of Saucon Valley by Professor Pazzaglia. So without any further ado, I will speak for about 15 minutes on the history of the discovery and then the history of the theft, and then we'll get into the good part of the presentation and learn about the geology of our area. So, please excuse me, I will be reading off a script because I don't want to forget anything. On Friday, November 10th, very close to this time of the year, 1978, a little over 46 years ago, news broke that fossilized dinosaur tracks had been found near Coopersburg. They had been discovered by an amateur paleontologist, James A. Jim Turner, Jr. He made the discovery about 7 months earlier while driving through Coopersburg along Route 309 and had stopped his car after noticing the type of rocks at the site. After exploring for a short time, he found a set of dinosaur tracks. He had previously found some tracks near Lansdale and knew what to look for. To quote Jim, "It was an incredible feeling to uncover something that no eyes had seen for about 200 million years. One track in itself isn't too significant because not much about the dinosaur can be inferred from it. But when we began to find tracks in a series and footprints belonging to 6 or 7 different species, I knew we were onto something." Initial reports stated that over 100 tracks were found with the potential for thousands more. What made the site unique was that the tracks were of more than one species and were uncovered and that they were in a long series. Turner described in the later interview that you could see one set of tracks change from walking to running as if the dinosaur were being chased. Articles from the time described this as the most significant discovery of dinosaur tracks in Pennsylvania since one made in York County in the 1880s. By the time the news broke, work had already been going on for some time at the site. Jim knew that he had to turn to others to help with the site, and he approached Lehigh geology professor J. Donald Ryan. Professor Ryan asked for volunteers from the department to check out the find, and he approached graduate student J. Michael Clinch. To quote Clinch, "Ryan came up to me one day in the department with one of the fossil footprints about as big as my hand. He said, 'How do you like this?' showing me the print. I was amazed and immediately interested when he told me about the project. With that, Clinch, pictured below with Turner and Ryan, became the project coordinator, and Lehigh became the center of the project. About a month after the dig began, Lehigh students were joined by representatives from Dickinson College, Princeton University, and the William Penn Museum in Harrisburg. During their work, they not only found tracks, but also bone and skin imprints, algae colonies, mud cracks, ripple marks, water channels, and plant and seed remains. There were several samples put on display at the now defunct Lehigh County Museum, which may have ended up at Lehigh University. However, there was to be no removal of the tracks from the site apart from these samples. And I can say that there are some at Lehigh University, and you'll see some of them today. While the excavation had been going on for some time, the news of the discovery of dinosaur tracks reaching the public made it necessary to protect the site. Upper Saucon Township soon erected a temporary snow fence, and police from Coopersburg and Upper Saucon, along with security from the property owner, began to patrol the site. Fleet Leasing and William Thayer, the property owner, became a supportive partner, later installing a sturdier chain link fence. Thayer also abandoned plans which originally called for an unclaimed freight business and later a restaurant to be built there. A foundation was started to preserve the site, and interest in a museum or university in preserving or purchasing it. As a harbinger of things to come, Jim Turner explained in an interview, "There's too much valuable material. A few greedy people could do a great deal of harm. Prints stolen from a site can hardly be meaningful to anyone. Any disturbance now can really cost us. It would be like ripping a page out of a book, stealing information." On November 20th, Dr. Donald Baird, at the time the director-curator of Princeton University's Natural History Museum, visited the site. Baird was a recognized authority in vertebrate paleontology. After visiting, he stated that the site was both valuable from a scientific perspective and from its potential for educational purposes. He suggested it would be a great site for, quote, "a county park or small-scale outdoor museum with trail-side interpretive displays and information." A side note to this story is that we have been told that well-known paleontologist Jack Horner was sent by Dr. Baird to visit the site. Horner served as the technical advisor for the first 5 Jurassic Park films, had a cameo appearance in Jurassic World, and served as a partial inspiration for one of the lead characters of the franchise, Dr. Alan Grant. It should be mentioned that when news was made public, dinosaur mania hit Coopersburg and the Lehigh Valley. While researching for this presentation, we found several tie-ins to the discovery. Oberholzer's, a local kitchen and interior business, which was located in the vicinity of the discovery, mentions their advertisement, "The gift of good taste is an ancient one. The dinosaur steps lead to our doors." We found a real estate listing which attempts to capitalize on the discovery, and a holiday gift guide mentioned purchasing wood dinosaur kits. All of these appeared in December of 1978. The cartoon above appeared in November of 1981 after similar tracks were discovered in Limerick, Pennsylvania. A dinosaur even found its way onto our Coopersburg Historical Society emblem. Last is one article mentioned, "Sesame Street once did a 30-minute educational show about the site. We found no evidence of that, but we'd love to prove it happened and watch that show." Given all this excitement, it is surprising to learn that this was not the first time fossilized dinosaur tracks were discovered in Coopersburg. They had been discovered at least 20 years earlier. During our research, we found a newspaper article from November 1957 which interviewed Dr. Bradford Willard, a longtime Lehigh University professor of geology. You can see a theme with Lehigh University. As he mentions, the rock formations of our area were favorable to the preservation of these footprints, and specifically mentions that dinosaur tracks had been discovered outside of Coopersburg. We have no way of knowing if anyone remembered this earlier discovery, but it was never mentioned in any subsequent article. Once news of the site was out, the challenge was to preserve and protect it. Jim Turner initially worked to raise funds and lobby for either a university, state or local government, or some other organization to purchase and preserve the site. There were discussions to build a shelter, and research continued for some time, but eventually slowed down. In the meantime, the owner of the property, William Thayer, became an informal curator of the site. He agreed to stop all plans to build and erected a chain link fence around it. One of the employees at Fleet Leasing, Al Clan, studied up on dinosaurs and became the informal tour guide of the site. Over the years, interest in the site declined and it became overgrown and neglected. Groups from several local universities and schools would occasionally visit to study the site. The picture here, which may be a little tough to see, is from the Southern Lehigh School District newsletter and shows Mr. Impink's Earth and Space Science class visiting soon after the discovery. Mr. Impink, who shared the photos with us, believes the expressions on the students' faces were either disinterest or annoyance at the weather that time of the year. Apart from some visits like this one, by the end of the 1980s, the site was largely forgotten. Two views were now developing, one of the discovery's value and one of its unkempt nature. To quote Joseph Gerenscher, a Moravian University professor, "The true value of the prints would be more appropriately measured in the stimulated imaginations of the spectators at the natural site where, when they put their hands in the prints, they realize that they are at the same place, and only the passage of time separates them from something that was to become awesome and dominate the Earth's land surface for many million years. Another viewpoint is found in the quote from a developer, "What's there that's worth preserving? I go through Coopersburg every day and see where the dinosaurs walk through. It's all fenced in and the weeds are growing higher every day. That site is nothing but an eyesore." On Wednesday, June 21st, 1989, news broke that the once famous dinosaur tracks on the hill outside Coopersburg have been stolen. In a fleet leasing staff meeting on Monday, June 19th, the sales manager asked about the group that was working on the site of the dinosaur tracks the day before. It was soon realized that the group was not part of an official dig and had been stealing the tracks. Investigation found that on Sunday, June 18th, in broad daylight, a group of men had cut the best tracks from the ground, forever altering the site. Since this was in the middle of the day along a busy highway, there were plenty of witnesses, but their description of the vehicles and the men differed. It was determined the men had entered through a section of chain link fence, which had been damaged a couple of years earlier in an accident, and used heavy sawing equipment to cut out the best sequences of tracks and load them into their vehicles. Peter Larson, a fossil dealer, explained in a newspaper article that the tracks had little commercial value and that their true value was in their location. Estimates at the time that the individual tracks were valued from $10 to $100, and a whole sequence could be no more than $1,000. The prints were likely sold to collectors and were never recovered, but one later news article states they were traced as far away as Japan. The men who stole the tracks were also never found. If you have any leads, you can contact Upper Saucon Police Department. Right after the theft, there was a heightened interest in this site. The public was shocked, saddened, and some outraged. Don Heinzelman, then president of the Wildlife Information Center in Allentown, is quoted as saying, "It's really tragic that the people who should be concerned are apparently doing nothing." Lehigh County Commissioner Ken Moore worked to find parties interested in restarting activity at the site or excavating the remaining tracks before any development. And later in 1991, the Pennsylvania Historical and Museum Commission passed a resolution to encourage the preservation of the site, but ultimately this was only guidance as the land was private. Jim Turner, who had first discovered the tracks, tried to regain interest in the site again in the late 1990s and early 2000s, but ultimately nothing came of these efforts. Today, the unassuming site sits vacant along the northbound lanes of Route 309. If you blink, you would miss the overgrown area with the damaged chain link fence. Knowledge of this discovery is starting to fade in our area. However, the opening of the Saucon Rail Trail, which passes very close to the site, may help renew interest. The future of the site is uncertain, but according to the man who first found those tracks, the site still holds value. To quote him, "It got abused, it got beat up, but it's still preservable." With that, I would like to thank you all for listening, and I would like to turn it over to Dr. Pazzaglia.
Quick question.
Oh, yes. Any questions?
Who owns the property now?
That I'm not entirely sure of. I don't think it's an individual. I do think that it might be LLC or private concern. Yes.
How many of the tracks were probably lost during the excavation for the railroad and 309?
We were told by somebody who lived in the area at the time that when Valley Manor across the street was built, there were also tracks found, and you can only imagine that that whole area probably has something. Maybe it's not as significant, but yes.
You mentioned that somebody had stolen the best tracks there, and then after that you had the thieves were never apprehended, nor were the tracks apprehended, but also the prints. Did you have prints made after they stole the tracks? What do they come in, the prints?
The like molds of the site?
Yeah, mold.
I don't know what was taken of the site before it was damaged. I know there are still tracks there. A lot of the best ones were taken. And then there are some limited samples here from when Lehigh University and Dickinson and Princeton were working at the site. But we might learn a little bit more when we hear the rest of the presentation.
Another question, if you may, please.
Sure.
These dinosaurs that were in this particular area, Had they been there for a while? Were they passing through, up or down the continent, or?
I heard they were
What
going on
was the
vacation.
status?
I heard they were headed down to the shore.
That is a question for part 2. Yes.
The tracks that are remaining, since they're not covered, will they be lost to the freeze-thaw cycle
I'm not
and
in.
begin to exfoliate or break away?
Might be a good question for Frank. I do know they used to cover them. At least some of the articles stated that.
Yeah, those are some points that I'll cover in my talk.
Okay.
Or I'll try. I'll do my best.
With that, I will take a seat and bring up part 2.
Thank you very
much.
much. Well, welcome everybody. Thank you all for being here. My name is Frank. Please just call me Frank. It's a little bit humbling and very awesome to see another packed room. We had a packed room here in March, and now we have another packed room here in November. This is great. We're right after lunch. I do not, and the room is warm. I do not want to put you to sleep. So I'm going to do my very best to keep you engaged, but one of the ways to make sure that we have a nice engaged discussion is that you should not feel intimidated in asking a question. So as I go through the talk, there's going to be several places where I will pause and I'll say, this is a good place to take a break, and we can discuss some of the things that we just talked about or just heard, and then we'll move on. But if there's, at some point, if I say something that says, wait a minute, that requires further explanation, will you help me out with that? Please raise your hand and we'll do that. On the tables that are out here, I put some examples of fossils from our fossil collection at Lehigh University. I guess I should mention that. I'm a professor at Lehigh. I've been at Lehigh 26 years now. I passed my 25-year anniversary just last year, and I received a belt buckle. No, it was something along those lines. Prior to that, I was an assistant professor at the University of New Mexico in Albuquerque, and prior to that, I was a postdoc at Yale University, and prior to that, I was a graduate student at Penn State. I grew up here in northeastern Pennsylvania, so coming back to Lehigh to pursue a professorship in earth and environmental sciences was a little bit like coming home, or at least close to home. So in our collection at Lehigh, we have a lot of different fossils from a lot of different rocks from across the entire span of Earth's history. And the dinosaurs that we're going to be talking about today occupy only one part of that slice of life through the entire historical story of the Earth. On the tables out here, I put some examples of fossils that have little to do with the dinosaurs. Just some examples of fossils, the evidence of life on our planet from the deep geologic past. Up front here, most of what is up here, with the exception for what's in the box, most of what's up here is directly related to the dinosaur footprints here in Coopersburg. In the middle of the table, and I point this out so that later after the talk, if you want to come look at this, in the middle of the table are samples from the site that were collected and ended up in our collections. All of this happened long before I came to Lehigh. So I don't know exactly how they ended up in our collections. I have been doing my best to curate them, and many of these I use when we're teaching courses and so on. At the ends of the table, both right here and over here, these very large slabs, these are also excellent examples of dinosaur footprints of the same kinds of animals, the same dinosaurs that made the footprints here in Coopersburg, but these are actually from Connecticut. And so there is a wonderful site in Connecticut. It is called Dinosaur State Park. And it accomplished exactly what Alex was talking about, was that at the time, when the dinosaur footprints were discovered here, the idea was this would be a great educational or public outreach sort of opportunity. Make it into a park, you could have trails, you could educate. Well, this was done in Connecticut. It is a beautiful state park. I really encourage you to go there because it's impressive. And the prints that are there include many of the kinds of prints, the same kinds of animals that were here at Coopersburg. So that's just a little introduction to what's up here on the table, and hopefully at the end of the chat, at the end of the talk, you can come up and look. Alex said he was going to talk only for 15 minutes. I'm in my first of 15 hours. Okay, so hopefully, but not really 15, but we'll go. No, I'll keep this. We'll go as long as you guys want to go. How's that? My talk is spread into 3 parts. The first part is just a little bit of classroom education so that I could try to convince you that our planet has a very deep time history. And it's not that hard to listen to it. You just need to know how to listen to it. And I'm going to tell you how we try to teach students in earth and environmental sciences or in geology curricula anywhere as to the clues, the things that you would look at in the rocks so that you could learn to read its history. So we'll take a break. And then we will talk about what was going on here in Coopersburg something like 210 or 215 million years ago. And this picture, this is a beautiful, beautiful artistic rendition of what the world looked like up and down the east coast of what is now the United States about 210 million years ago. Okay? And I'm going to show you, I'm going to try to convince you that I can take you to parts of our planet today that look similar to this. The vegetation would be a little bit different, but very similar to this, and try to make create a mental image for you all so that you kind of know what Coopersburg used to look like as opposed to what it looks like right now. You will notice there are no pizza shops in this rendition, right? But which is a tragedy because pizza is good in any era, right? It doesn't matter where you are. But I want to point out that I'm going to try to convince you that there's places on the planet today that look actually quite similar to this. And this is one of the key things that we do as earth scientists. We say that the present, we have a saying, we say the present is the key, or maybe we can say the keyhole to the past. It gives us a model, it gives us a starting point so that we can understand what our planet used to look like in the past. We look around us today and see what does it look like today, and can we recreate those environments as we go backwards in time. Then we'll take a little pause, and we will talk specifically about the dinosaurs. So if anybody's here to hear about dinosaurs, the last third of the talk, we're going to talk about dinosaurs, okay? Because I know everybody thinks that they're cute and cuddly and all the rest, and they are kind of cool. So we'll talk about dinosaurs at the end of the talk. Okay, so here is the approximate location of the site. This is just out on Route 309, and you can see I'm pointing out the rail trail, right? So now getting to the site from the rail trail is quite easy. Getting to the site from Route 309 is quite dangerous, and it is on private property, so you're not supposed to go to the site. But one of the points I'll be trying to make is that the site is basically flat slabs, very similar, not dissimilar from the pieces of rock that I have here. And it's the top of the sedimentary beds that contain the footprints. So if you go to the rail trail, what you're seeing at the rail trail is a vertical slice down through those rocks. And potentially, every layer in that slice is potentially a layer that could harbor footprints, right? So one of the questions that came up, someone asked about weathering and whether the prints that are there now can be preserved. I've been to the site, it's very underwhelming as to what is currently still there in terms of footprints. There's some beautiful examples of something called mud cracks, which are on a sample back on that table. There's some beautiful examples of things called wave ripples. But the evidence of footprints, there are some, but they're very underwhelming. They're not very well preserved. It doesn't mean that there aren't more footprints there. They just might be on the next slab underneath that would have to be lifted up and investigated. And so that's the that is the location. And Alex talked about this with when he was going through his talk when Mr. Turner discovered the sites. He said, "Imagine I got out of my car and I went up there and I found these footprints, and I was just so excited." This is something that I do with my students all the time. This picture is a picture from out in Wyoming near the wonderful little town of Tensley, Wyoming, and that's my rock hammer. And this is not a picture just of my rock hammer, although my rock hammer is very photogenic, as you can see. My rock hammer, I would always tell to the students, I know that this section of sedimentary rocks harbors many dinosaur fossils. And I said one year to my students, while we were out there, I said, who feels lucky today? Who's gonna go find something? And within 15 minutes, a student was yelling, I found something, I found something. I'm like, oh yeah, what did they find now? And sure enough, the orange, this, what you see right here, that layer right there, and all that broken material, that's all bone, that's dinosaur bone, right? And so this is part actually of part of a dinosaur arm bone going up into the shoulder. And it was probably from a sauropod. And we've been back to this site many times, and every year there's a little bit more erosion, and some of this old bone is washed away, and some new bone is found. Eventually this will disappear, right? Unless somebody actually comes and collects it and preserves it, it'll eventually disappear. But some new bone will be exposed somewhere else, because there are some sedimentary rocks that harbor this. And I'm not doing this to gross anybody out, but I did bring some bone with me. You come up here and look in here. This is not dinosaur bone. This happens to be part of the jaw of a pig that was very common in the western United States. If you ever go to Badlands National Park, you just trip over fossils in the Badlands. It is just, you cannot go to the Badlands and not find a fossil. The stuff is just everywhere. But one of the ways that you know that you have found the bone, if you find something suspicious like that, find something suspicious like this, and that's got teeth sticking out of it, so that pretty much gives it away. But bone is sticky to your tongue, right? My tongue is sticking to that because it's porous. And so if you're ever like out and you see a bunch of geologists chewing on rocks, you know what they're trying to do. They're trying to find out if they just found some bone, right? And so that. But now that I licked this, please do not come on. Please. And this is being recorded. This is horrible. Okay, so one of the main principles that we use in geology to describe sediments and sedimentary rocks, which are the only rocks that harbor fossils and harbor life. Imagine there's three main kinds of rocks out there. One of them is sedimentary. What are the other two? Who knows what the other two are? Metamorphic and igneous. Okay, so igneous comes from born of fire. Okay, living things are not living in melted rock, right? Like, life has found a way to live just about everywhere, but at temperatures of 1400 degrees centigrade, not real good for life. So you don't find fossils in igneous rocks. However, you will sometimes find casts of living things in igneous rocks, like trees that have been overrun by lava, or trees that have been overrun by ash, or people that got buried at Pompeii by volcanic eruption. So you do sometimes find it in those environments, but generally speaking, living things don't live in igneous rocks. Living things really don't like living in metamorphic rocks, because if you take some other rock, you make a metamorphic rock out of it, what you have to do is cook it and put it under lots of pressure, very deep in the Earth's crust. And again, that's not an environment where you're finding living things. So you don't typically find fossils in metamorphic rocks. You do find fossils in sedimentary rocks, right? That's where the history of life on our planet is preserved. And one of the principles that we use is the principle that when you make a sedimentary rock, that sediment starts out flat. So when you make sediment and you transport it and you deposit it in a layer, and the layer starts out flat. The other rule is that layer is laterally continuous, and the other rule is that the layer at the bottom is older than the layer at the top, right? That makes lots of common sense. And so when we always talk about, hey, how old is something, essentially what geologists have been doing for over 2 centuries now has been documenting these layers and documenting which layer is on top of the other layer. And so we have this integrated history of the oldest layers that we know of, and then layers of middle age, and then young layers. And this is a global effort. It's not just what we've done in Pennsylvania or what's been done in Coopersburg. It's done globally. Okay? So this is one of the basic concepts of something that we call stratigraphy. And one of the best places to do that, let's transport ourselves for just a moment to the Grand Canyon. Okay? Because in the Grand Canyon, you have this incredible history of these layers of sedimentary rocks that sit on top of older igneous and metamorphic rocks, which are part of the backbone of the North American craton, or North American continent. And then there's layer after layer after layer of sedimentary rock. And for the Grand Canyon, this part of the world, these layers have never been significantly deformed. They've never been tilted. They've never been turned upside down. They've never had something come on top of them. The only thing that's ever happened is, thankfully for us as geologists, the Colorado River carved this huge canyon right down through them. So you can see, it's like opening the pages of a book. It's like taking a book and opening it up, and you can see each one of those layers is telling us something about Earth history. And in the Grand Canyon, this oldest layer down here, it's called the Tapeat Sandstone. It's 540 million years old. And so then all of these other layers that you have on top get younger and younger and younger. And these layers contain evidence of life, right? So up here in this layer that's called the Coconino Sandstone, it has these incredible footprints of reptiles running around. As it turns out, the Coconino Sandstone is an ancient desert, and there's these big sand dunes, and there were these reptiles and lizards running up and down these sand dunes, and you could see that preserved at the Grand Canyon. You don't have to look hard for this. On almost any trail you take in the Grand Canyon that takes you through the Coconino Sandstone, you'll find footprints. You don't have to look hard for them. They're very common. However, down very deep in the Grand Canyon, on some of these oldest layers, the only evidence of life down here, not footprints, there's no evidence of plants. The only evidence of life down here are these simple algal mats, these things called stromatolites. And I brought an example of a stromatolite. It's sitting on that table right there if you want to see it later. So one of the things that we see as we go through these layers is that the oldest layers contain evidence of simple life. And then as you go up through these layers, that life evidence gets significantly more complex, and we start recognizing things that say, oh, this is an animal that has legs, right? Or this is a reptile, or this is a mammal. And then ultimately, the layers right at the very top contain things that we really would recognize. This is a cow, this is a cat, this is a dog, this is a human, right? So these are this is the way that geologists put this story together. And I would say that it leads to a concept that we call biostratigraphy, which is learning the layers, learning the strata on a biological perspective, right? Because we can see how life is changing through here. The names that you see on the left, we commonly see this. What's your favorite of all-time movie about dinosaurs? Jurassic Park. What does Jurassic mean? Silence, right? What does Jurassic mean?
Time period.
Okay, so it is a time period, right? But why is it called Jurassic? Why didn't I call it Fred or something like that, right? Why is it called Jurassic? So there's a place on the planet called the Jura, or the Jura Mountains. Where are they? Does anybody know?
Russia. Europe.
In Europe, they're in Switzerland. Okay? Okay, the Jura. So it's just north of Zurich in Switzerland, and it turns out there that there's a sequence of rocks there that contains a very characteristic suite of fossils that geologists at some point during this history of creating the strat column said, we're going to call this the Jurassic, and the name for the Jura Mountains. Because there's a suite of fossils there that looks like nowhere else in geologic time. Similarly, there's this word right here. Let's go with Devonian. This might be easier. Devonian. That's named for Devonshire, England. Okay? Because there's a place in England, Devonshire, that contains a suite of fossils that defines an ecosystem of life that existed only at that time in Earth's history. And the ecosystem of the Devonian is fundamentally different than the ecosystem of the Jurassic. So as we see these ecosystems come and go, we give that ecosystem a name. And that's where these names come from. Where do you think the type section for the Pennsylvanian is? We're here it is, right? It's in the state of Pennsylvania. Right? So the Pennsylvanian ecosystem that led to the term the Pennsylvanian time period comes right here from Pennsylvania. Okay? And just to play with some of the other ones, like Cambrian, that's for Cambria, not England,
Canada?
Wales. Right? So Great Britain, to be fair, but Cambria is in Wales. Right? So that's where a large part of this naming came from. And what's amazing about it though is that imagine you go back to the 19th century, the early part of the 19th century, when geologists were first working this out. Imagine that you're in a place like Cambria, Wales, and you define this ecosystem of fossils based on the fossils you find there. It turns out that exists everywhere across the planet for that time period, right? Which to me is really amazing. Like, who would imagine this little obscure place of Cambria, Wales could be representative of something that exists globally? And that's true of all these time periods. So when geologists first put together the geologic column, so here's the geologic column and nicely in color, there's really two things represented more than anything else on this geologic column. It is, each one of these names represents a time during the history of the planet when there was an ecosystem and there was an assemblage of animals and plants and microbes, and it was an ecosystem, and it was functioning and it was harmonious and everybody was happy. And then when you change from one of these names to the next one, which is the period of time between the time periods, something very dramatic and bad happened. For one ecosystem to basically go away and to be replaced by a new one. And what do we call those?
I don't know, but do these time periods last about the same amount?
No, and that's unfortunate because on here, these colors, that's not, I'm not sure that the thickness of the box is scaled correctly to the time. That's just so it could fit on the page. But you can see the amount of time in between there. But it turns out that they're not the same. Some are much shorter than others. What do we call it when life is doing just fine and then something over a short period of time makes that life go away? What do we call that? Extinction, right? An extinction event. And on this strat column, there's at least 5 or 6 times when there's been not only an extinction, but a mass extinction. Something really, really bad happened that caused lots of life to go extinct. The most dramatic one on this column is right here at the end of the Permian. 248 million years ago, 90 to 95% of all the life, particularly in the ocean, went extinct. Okay? 90 to 95% of all life gone. And then what happens when you come through one of those bottlenecks, one of those biological bottlenecks, is that life has to reinvent itself, right? And so it begins to radiate out and reinvent itself, and old animals and plants that were doing very well get replaced by new forms. The dinosaurs were both the beneficiaries of that, as well as they became casualties of that. Because out here on this time scale, you see that what's called Triassic, 206 million years ago. That number is wrong, by the way. That number is actually 200.1 million years ago. But at that time, in the late Triassic, dinosaurs had just come into their own as a group of land animals, but they were not the dominant land animal, but they were here, and they left some footprints for us to look at. And then at that end of the Triassic into the beginning of the Jurassic, there was a mass extinction event. And lots of life went extinct. And one of the forms that did not go extinct were the dinosaurs. So after that mass extinction event, the dinosaurs really were able to occupy the vacuum that was left by all of these other forms that had gone extinct, and they radiated and they became the masters of the rest of this time called the Mesozoic. So Jurassic Park, in the Jurassic, if you were a dinosaur, you were top dog, right? If you were something else, you were an underling. But then by the end of that time period up there called the Cretaceous, 65 million years ago, there was another mass extinction event. And this time, the dinosaurs ended up taking it on the chin. And they did not make it through that mass extinction event. Other animals, namely mammals and birds did. And so now we're living in a world dominated by mammals and birds and no dinosaurs. Because we were the beneficiaries of that mass extinction event. Yes?
Do we know the cause of the Permian mass extinction?
It's highly debated, but it's very, very likely that it was massive outpouring of volcanic rocks of what we now today call the Siberian traps, which are in northern Siberia. So most people are zeroing in now that it was a volcanic cause. Okay. So with that, we can take a pause and have some questions before we go to the second part. You guys all understand stratigraphy now? You all good with that? Yes?
Are you going to find the same dinosaurs all over, or they're like specific dinosaurs?
You will find the dinosaurs will change from place to place based on the following. Number one, where you are in time. So if you look at the movie Jurassic Park, and I honestly, it's been so long since I saw the original Jurassic Park, and then I didn't see any of this, so I don't know how accurate they are. But if you look at the forms that are in the movie Jurassic Park, they would be dinosaurs that occupied the planet during the Jurassic period globally. And then the only thing that would change is that some of those dinosaurs probably were better adapted to wet versus dry climates, or colder versus warm climates, just like animals are today, just like mammals do today, right? So, but the overall assemblage that represents Jurassic dinosaurs would have been globally distributed. When you go to the Cretaceous, still lots of dinosaurs, but they were different, right? And we'll get to this later, but everyone's favorite, who's everybody's favorite dinosaur of the Cretaceous, the big scary one that kids love? T-Rex, okay? T-Rex is a Cretaceous carnosaur. It is the scary dinosaur of the Cretaceous. Were there any T-Rexes in the Jurassic? No. What was, the T-Rexes never saw the Jurassic. There was something before T-Rex. What was the carnosaur of the Jurassic? Allosaurus. Allosaurus. Okay? So same function, big and scary, but different animal. Okay, yes?
So I'm trying to understand how the fossil bed that we're talking about was created. So a dinosaur, of course, something heavy compacted earth. Now for it to be preserved that way, something soft had to cover it, right? And not be as compact.
Ding, ding, ding,
So
ding.
what happened there?
You should come up
Did
and
it,
give
is
us
that
a-
where it rained? Is that the evidence of a raining of soil?
Absolutely. And we're
All
gonna-
over the place?
Well, not all, but here. It
Well,
had
a
to-
lot of places.
Lots of places, exactly. So this is great. Did everyone hear this question? Or everyone hear the comment? The question and comment is the following, is that there must have been, if you believe me that there's a footprint right here, right? If there's a footprint on this rock before it was a rock was just soft sediment. So a dinosaur comes walking across here, squishes down and puts a footprint in there. And now for this thing to be preserved, what I have to then do is pretty quickly after the dinosaur walks here and makes the footprint, I want to cover this with another layer of sediment.
And all of the earth around that print.
And all the
Which
earth
was
not-
more solid than what's a
That's exactly right. That's exactly right. So remember what I
hard to
said.
imagine.
Remember what I said one of the rules was that sediments are laid down flat, they're laid down regionally, right? And the lowest ones are the oldest and the ones at the top are younger. So regionally, not just at the precise place where this dinosaur walked, but imagine all of Coopersburg, after this dinosaur did this, was probably covered by a layer of sediment. So tell me, you guys tell me, where would you be? Where would be a logical place where that's happening? Like today, like where would you go today to see a place where animals might be walking around on soft sediment, but that in a pretty pretty short period of time gets covered by new sediment? Where?
Louisiana.
Louisiana. What is Louisiana? Really good Cajun food, right? But what else can we have in Louisiana? The whole Mississippi Delta. So river deltas are great places for this to happen because rivers are bringing new sediment down all the time, right? Everybody knows the story of great rivers that flood annually so that there's new fresh sediment for farmers to put their crops in, like the river Nile was commonly used this way, right? That rivers particularly rivers in more arid regions where you don't get a lot of rainfall, but every year you can count on them to flood and put in a new layer of sediment. So if you happen to be walking across the floodplain of a river the day before that flood comes, your footprints have a good chance of getting preserved. Right?
Wouldn't plant life growing, dying, lying down, be part of that accumulation?
The question is, wouldn't plant life, growing and lying down, become part of that accumulation? Is that enough physical evidence of that happening? So the Pennsylvanian, so much plant life died and got laid down, and it accumulated so thick, we went and mined it. What are we mining? Coal. Coal is just dead plant life, right? That's all it is. In fact, it's so much plant life that there's no sediment in between it, such that it's just pure carbon and you're burning it, right? Right? So it's great point. Great point. Exactly. So right. So you'll get environments where the plant life will do exactly the same thing. Now look, this point. I hate you for asking that question because it sounds like I made it sound simple, right? It's actually more complicated than that. And there's some very weird things out there that I really don't fundamentally understand, and I press my paleontologist friends on this all the time. Because I brought along this thing, and some people were looking at it. This is a vertebrae, part of a vertebrae, from a tail of a whale. And I found this down at Calvert Cliffs, Maryland, which is a great place to go find marine fossils of Miocene age. So this thing is about 15 plus or minus million years old. And this is an early whale. Now, this whale died 15 million years ago. And again, so this fossil preservation thing is a little bit, in some places, easy to understand, and in other places, a little bit harder. So this whale died 15 million years ago, and its bones got scattered on the seafloor. And this thing, for it to be preserved, it would have to get buried pretty quickly. Otherwise, if it's left out on the seafloor surface, it's going to decay just like our bones decay when we die, right? So we put ourselves in caskets, we are pretty much assuming that we're never going to get preserved. Right? We're not. That's not a good way to preserve us. If you want to get preserved, go get buried under sediment real fast. You want to be eternalized, go to the Mississippi Delta. You'll have a much better chance down there. Okay? But the layer that this came out of was only about as thick as the bone is in the first place. And I thought to myself, how do you do that? Like, how do you, how do I just get so lucky that the layer that preserves this just so happens to be about as thick as this bone is in the first place? So, what's that?
Black flood.
Well, it was something that happened quickly for sure. But there's just a lot of details about fossil preservation that people are still fundamentally researching because sometimes it's easy to imagine, other times a little bit more difficult. But there's the physical evidence. It happened. I had an old professor at Lehigh who would always tell me, he would say, if you see it, it must be possible. Just because you can't figure it out means you're a dumb, right? But if you see it, it must be possible. I guess so. Other questions?
Is the timeline that you went through, is that been standardized for quite a few years, or have there been updates?
So this is a great question. The question is this now like canon? Is this standardized, or is it constantly getting updated? It's the latter. This is constantly being updated. What has become largely standardized are these names. And so the names and the order in which the sediments come, that was established well over 100 years ago. What keeps getting changed are these numbers, like where you are in absolute times. Because remember, the early geologists, they might have been able to define a series of fossils that they called Jurassic, but they had no idea how long ago that was, right? And they were living in a world where predominantly you had to fit everything into 6,000 years, because that's what the Bible said, right? So they were like, there's this thing called Jurassic, but I really have no idea where I am in time. And it's been since that time that the numbers, like where you actually are in absolute years, that keeps changing. So on here, this says 540. We now know that number is actually 541, right? And so we keep changing those numbers. Yes?
Is that because of the radiocarbon?
Well, it's from radiometric dating, but we'd never be able to use radiocarbon that long ago because the half-life is too short. But there's other uranium, lead, and rubidium, strontium, and argon that we can use to get us back into these older time periods. Other questions? These are great questions.
Yeah.
Go ahead.
What kind of animals are you talking about?
Yeah, great. You guys are great. Somebody, could you hand me this?
I was raised on here.
No, that one. Next one. You were raised in Cambria, Wales?
No,
Oh.
I'm raised right here, and that's when I was living on a farm, so, this is a little bit different to me, because, we had all kinds of stuff. And it's like, okay, what kind of animals are we talking about?
So the kinds of animals down here, all the way in the Cambrian, the Ordovician, Silurian, Devonian, were they're all marine. At this time during Earth's history, nothing was living on land yet. Maybe some insects, a little hard to know for sure, but all life was only in the oceans. And so I brought along a nice sample of This is from the Devonian of Pennsylvania. It contains all sorts of things that look like seashells, but they're not exactly seashells. They're things called brachiopods, right? Today's seashells are called pelecypods. These are called brachiopods. They were an ancient form of a seashell, and they're very common in Pennsylvania. So, answer your question, what did life look like down here in the bottom part? It was all marine life. And plants didn't make it onto land until the latter part of the Silurian and then in the Devonian. And then in the Pennsylvanian, they went crazy and made coal. Okay, so many of them. And then you start recognizing things again that you would recognize, certainly mammals, not until you get all the way up to the top in the Cenozoic. And in the Mesozoic, that's the dinosaur time. Right? That's when we have lots of dinosaurs. Okay. Other questions before we move forward? Because now let's talk about Coopersburg 210 million years ago. What did it look like here? Oh, no, the wrong way. Okay, so this is not Coopersburg. This is the state of Pennsylvania. Coopersburg is right here in the circle. And this is a great, every state in the United States publishes a map that looks like this. This is the geologic map of Pennsylvania, and all of the really impressive colors, the beautiful colors, each color represents a different rock from somewhere in that geologic column. Okay, so on this map, and I don't know why they did it this way, but on this map, this green color down here, these greens and yellows, that color in real color to our eyes is red. So all of this reddish or brownish red or maroon colored rock that has the dinosaur fossils in it, on our geologic map, it's colored green. And you can see there's a swath of it that starts right here as Coopersburg from the Delaware River, goes down across the Susquehanna River, and then down into Maryland. Right? Do you notice that there's a bright orange squirted into that green color right there? That bright orange is an igneous rock, and if you want to go see it, there's plenty of opportunities to see it around here. How many people have been to Ringing Rocks County Park? Okay, that's the rock at Ringing Rocks County Park. The stuff that rings real nice. Okay, it's an igneous rock, it's called diabase. And we're going to see how it fits into the story of what happened here at Coopersburg in just a moment.
That's not argillite?
No, that at Ringing Rocks is not argillite. Ringing Rocks is diabase. Diabase.
You find that in the river too.
And the Delaware River?
Yeah.
Yeah, oh sure. Sure, especially where it outcrops right on the, and so for reference, Ringing Rocks, I have a pointer here. Ringing Rocks is right there. Okay, that's Ringing Rocks right there. Okay, all of the other colors on here represent rocks of different ages. And in Pennsylvania, the oldest rocks in Pennsylvania that represent, you're down here very low in the stratigraphic column, or you're even on the igneous and metamorphic rocks that make up the kind of the core, the foundation of the continent down here. Those oldest rocks are found, first of all, in these pinks and I don't know whatever color that is, light yellow, down here close to Philadelphia. And in addition, they're also found right here in these pinks, right here. So just on the other side of Coopersburg, the hill that Lehigh is built on goes by the name South Mountain. Okay, so those rocks under South Mountain are going to be these things way down here, and they don't contain any evidence of life because they're too old, and even if they weren't, they're metamorphic and igneous, and so we don't see any evidence of life there, right? And then just when you come from Lehigh's campus, from South Mountain, and you come over to Goodman campus, like where the football stadium is, right? That we call the Saucon Valley, right? Okay, so you come into the Saucon Valley, and then you come down into Coopersburg, you very quickly transition from these rocks right here, believe it or not, all the way up to the very top, right here. Okay? And all of this stuff in between is largely missing. Here, it's in other places, it's in the Lehigh Valley, and it's in other places. I'm gonna show you that on a little cartoon here in just a second. But you very quickly go from the oldest rocks in the state to the youngest. Right here, which is really pretty cool.
Is that because of glacier?
It's not because of
That was
glaciers.
my question. Glacier.
No, it's because of a fault. And I'm gonna show you in a cartoon how a geologic feature called a fault cuts out all of this stuff and puts those rocks right there in contact with those.
Like a sudden cavity?
It's not a cavity, it's a break. It's a break in the Earth's crust. I'm gonna show you on the cartoon.
I would have guessed it was a river.
Nope, I'm gonna show you on a cartoon. Watch. Let's see if this works. Okay, it's like this. So here, imagine what I've done here is there's Coopersburg, okay, and then this right here is the Saucon Valley, and then this pink stuff right here, that's South Mountain, and then up here, this is the whole Lehigh Valley, right here. This blue color right here, that's the cement belt. That's rock, that's what's being mined to make Portland cement, okay? And then up here, this brown right here, that's what we sometimes call, I don't know, depending on where you're from, you can call it Kittatinny Mountain, or you can call it Blue Mountain, or you can call it First Mountain, depending on where you're from. Or if you grew up in the Lehigh Valley, you say that's North Mountain, because it's the mountain to your north, whereas this one is South Mountain, because it's the mountain to your south. But that's the Lehigh Valley. Kittatinny Mountain, that would be like Lehigh Gap, okay, or Palmerton, that area. And then you come down here, this is all the Lehigh Valley. Bethlehem and Allentown would be out here. And then this is Lehigh's campus right here. This is the Saucon Valley, and then here we are at Coopersburg. All right? Now, on the bottom cartoon here, what I've done is I've taken a knife, and I've sliced down into the ground, and I'm now looking at that slice. So, there's Kittatinny Mountain, and now we come down into the Lehigh Valley. There's the Lehigh River, would be flowing in that little ditch right there. And then here's South Mountain, and then here's the Saucon Valley, and then here we are at Coopersburg. And where we are at Coopersburg, there is a giant fault that has taken this piece of crust and dropped it down, that's what that arrow there means, with respect to everything else. So the older rocks are going to be found on the left-hand side of that fault, and that's true. Here's the older rocks of the Saucon Valley, South Mountain, and then into the Lehigh Valley. And the youngest rocks are going to be preserved here. Right? Now, again, so look at this concept. Sediments are deposited flat. So I deposit the sediment flat, and then that sediment sinks a little bit, and I put another layer on top. And that sinks, and I put another layer on top, right? So the place where you're doing that is called a basin, just like we would like a sink basin. It's a hole that you're putting sediments into, all right? And so if I could make that thing sink down, I could preserve the youngest stuff that's at the top. If I can't allow that thing to go down and sink, my young layers at the top are going to get removed by erosion. So over here, so trust me, there was a time in the past where all of the rocks here that are colored in red and represent the rocks that have the dinosaur footprints in it, they used to be over here too. But they've been stripped away by erosion, because this fault took these rocks and dropped them down here, and it took the same rocks over here and pushed them up. And when they went up into the air, what happened? Erosion took them and washed them away. Okay? So all of us, like even over the top of South Mountain, would have been the same rocks that preserved the dinosaurs, but because they ended up on the wrong side of that fault, they got removed. And so the only part of Pennsylvania that preserves rocks that have the dinosaur footprints in it have to be on the right-hand side of that fault. That fault's called the border fault. How many people raise your hand? I think it was would have been maybe March or April of 2024. Did you all feel a little earthquake? Where was that earthquake? Remember where it was? It was in New Jersey, but that's the fault that moved. That's the fault the earthquake was on. And so that fault is not what we would call today an active fault. It's not, it's really not active, it's quite geriatric. It's trying to remember when it was young and very active. And every now and then it reminds us, I could make an earthquake and you're gonna feel me. But in the deep geologic past, it was very active. It was very active, and I heard somebody saying, oh, like the San Andreas. Yes, it was very active, like it had a different movement on it than the San Andreas, but it was very active. It would generate huge earthquakes, and that, and quite honestly, was the time the dinosaurs were here, right? And so the dinosaurs were feeling lots of earthquakes on that fault, trust me. Now, this is a complicated diagram, and I just want to point out, again, when I'm circling Coopersburg here, this is showing that basin. It's called the Newark Basin for Newark, New Jersey. It's called the Newark Basin, and it represents this big hole in the ground that sediments were washed into, and it was representing like a delta environment, among other things. Lakes, there were big, big lakes here, and it was a good place for dinosaurs to hang out. Evidently. Right? Now, the other part of this that I want to point out to you, and I have some stuff coming up, today, the Newark Basin today, on this map over here, every dark blue, every little bit of dark blue, that one, and this, all dark blue, those are all basins that contain rocks that look like this, and they all have dinosaur fossils in them, all of them. Okay? They represent a landscape that used to be here. It's not here anymore. I'm going to try to show you what that landscape used to look like. And at the time that that was here, this big ocean didn't exist yet. There was no Atlantic Ocean yet. It did not yet exist. The fact that there is a big ocean here right now testifies to the fact that the continents are not static. They dance around the Earth's surface, right? This thing called continental drift or plate tectonics. And the act of making a new ocean results in a lot of new volcanic activity. And the evidence of that volcanic activity are the rocks that you see at Ringing Rocks, the diabase. Okay, so that the physical evidence of making the Atlantic Ocean is right here in our own backyard. Okay, so where were we? We were right here. All right, we've already talked about this. Here are some of my students. Every fall, I put my students on a bike at Lehigh, and we ride the whole Saucon Rail Trail. And we look at the rocks all along the Saucon Rail Trail. And our last stop is here, right below the dinosaur footprint site. So right up here at the top of this picture, that's where the dinosaur trackway used to be. And so on the rail trail, there's a vertical cut, and now you can see a cross-section of the layers that the dinosaur footprints were made on, if you walk on the rail trail. And I had a student a few years back, as a project, put this sign together, and that's version 2 of the sign, by the way. So if you go there, you could read the sign. We had 2 versions of the sign. The first version was awesome because we actually took all of the rocks and we cut them out and we laid them into the sign. And we took this footprint right here and we made a cast of it and we put it right into the sign. And then about a month after we put it there, someone vandalized it. Right? It happened. And so then, and very nicely, an anonymous donor, we have no idea who this person was, because the sign cost the better part of $2,000, right? And so an anonymous donor came and said, I'd like to replace that sign. And so what we did was we made a new one, but I didn't go through the trouble of making the cast and everything. And then they put a plexiglass top over it, so it protects it. So you can go out there and read that. But I bring the students here, and they're learning all about these sediments of Triassic age, of dinosaur age. And the only way I can get them here, remember, these are college students. How do I get them here? What do you think other than the fact that we're gonna go look at this really cool site, we're gonna see like where the dinosaurs were. That's not enough to get them here. How do you think I get them here? Where do I go after this? We go to the inside scoop. That's exactly where we go. We go to the inside scoop, right? And they this year they murderized me because I said, we're gonna go to the inside scoop. Go in and get what you want and I'll pay for it. Well, they came up with sundaes, clothes, and everything else. I said, my wife's gonna kill me. I gotta go rob a bank to pay for it. Right? I thought like, they'd come out with like the single scoop. No, it's not single scoop. So these rocks are part of what we call the Passaic Formation. They're about 210, 215 million years ago. Old. All right, so what did the world look like? If we looked at our planet at that time, there's Coopersburg. All of this is what is to become North America. This down here is South America, and this over here is Africa. Up here is Europe. All right? So the continents looked different, because remember, the continents are always dancing around on the surface of the planet, this whole continental drift and plate tectonics thing. And on the other side of the planet, at the time that the continents looked like this, was a big global ocean, sort of the way the Pacific Ocean is today, but it goes by the name Tethys. And starting in the late Triassic, this big continent started to split apart. And so what was one big continental landmass, which goes by the name Pangaea, okay, global Pangaea, starts to break apart. And part of that breaking apart was big eruptions of a lot of volcanic rocks, and the evidence of those volcanic rocks are ringing rocks. And in fact, right on the rail trail, if you do this, I don't know, this is really cool. So I encourage you to do this. This is great. You could access the rail trail very close to this site. Do you know where the cement, is it cement factory or what?
Yeah.
Is it right? Is it Station Avenue perhaps?
Yeah.
So there's a rail trail access parking right there. You can park there, and in 5 minutes you can walk to this site. And then if you walk for 2 more minutes past the sign, you'll come to a part of the trail where there's a lot of, it's a boardwalk. Okay, like wood has been put down so that it's a boardwalk. Right at that point, you leave the sedimentary rocks and you pass into the diabase. You pass into the igneous rocks. So right there, you can see both of those things right there, and you can see the evidence of the ocean opening up, and you can see the evidence of this sedimentary basin. It's really quite nice. Very, very, very nice. Yeah, it's very, very easy to get to. At this time, Coopersburg, well, I'm going to go back a little bit farther. Here we are 280 million years ago. Coopersburg was on the equator, and it was in the middle of the continent. And this meant that it had a very seasonal climate. And so it meant that it had a very wet season and a dry season. It had a monsoonal kind of rainfall pattern. We don't have monsoons today, but at this time there was a monsoonal rainfall pattern. And then by the time you come into the Triassic, early Triassic, 245 million years ago, one of the things that you see happening is that there's these fingers of ground here that are starting to move towards Coopersburg. That is the Earth starting to crack apart and make these basins that are filling with sediment that are going to allow these footprints to get preserved. Okay? And now as you move into the late Triassic, here we are almost at Coopersburg, at the time of the footprints. Now these basins are full of lakes. It's a little hard to see in this picture, but there's actually lakes filling these basins. And then as you move further in time to the early Jurassic, now 195 million years ago, the crust has been pulled apart so far that you're now starting to make a linear ocean in here. And since that time, that linear ocean has just gotten wider and wider and wider, and today we call it the Atlantic. That's the Atlantic. And it's continuing today. So trust me on this. If you get in an airplane tomorrow at Newark Airport and you fly to London and you spend a year in London and then you fly back, on your flight back, you had to go 1 more inch to get back here. Because London and New York continue to get farther apart every year by about an inch. Okay. Question?
Did dinosaurs not exist back then?
So dinosaurs were existing now in the late Triassic and in the early Jurassic. They are on this landscape now. They are here. Okay?
So, sir,
And so this looks like, oh, question, go ahead.
as quick as possible, how come we don't find T-Rex bones here?
The rocks are not young enough. T-Rex lived in the Cretaceous. We
Oh.
need to get up into Cretaceous rocks. Now, to be fair, we have Cretaceous rocks all the way down on the coastal plain. In New Jersey, there's Cretaceous rocks, and right in far southeastern Pennsylvania, there's Cretaceous rocks, but we've never found T-Rex bones in there. We have found Cretaceous dinosaur bones in there. There's been some duck-billed dinosaurs found in New Jersey in the Cretaceous rocks, but we haven't found T-Rexes here. And in Pennsylvania, we just don't, the rocks aren't the right age.
So in the West, it's because of plate tectonics pushed them up?
It just, in the West, we had basins that were, in the same way here that we had basins in the late Triassic sinking to be able to preserve the early dinosaurs, we had basins in the western US that were sinking at the right time to be able to preserve.
But now they're like 5,000 feet up.
Exactly, and so now, thankfully, they're 5,000 feet in the air, and rivers have cut down through them, and geologists can go find the bones.
Oh, there you go.
Right? Right? Imagine how many steam shovels we would need to find this stuff if rivers didn't do the work for us. Right? Right? This is what the process looks like. You start like this, the crust starts pulling apart, you get these rifts filled with lakes, and then the lakes go away and you get a linear sea. Doesn't that look like the Red Sea? It certainly does. That's Egypt on the left and Saudi Arabia on the right. That's happening today in that part of the world. And then you end up with an ocean, and in this case would be the Atlantic Ocean. Okay, now check this out. This is Google Earth. So I went, everybody know what Google Earth is? Google Earth is how Frank spends all of his time when he should be doing something else. So like, you know, when procrastination takes control of me, it's Google Earth and a pizza, right? And so this is Google Earth, and I'm looking in Google Earth at a place called Death Valley, California. Everybody know where Death Valley is, right? Death Valley is a rift valley. This is a place in the United States where the crust is being pulled apart today, currently, just like it was in Coopersburg 200 million years ago. And I'm looking here, and you can see there's a big mountain range. These are called the Black Mountains. And then down here, there's a big basin that's mostly dry, because in case you didn't notice, if you've been to Death Valley, it's hot and dry, right? It's quite hot and dry. And between this big basin down here and the Black Mountains, there's one of these faults that there's earthquakes on all the time. Okay, very common to get those earthquakes there. So there's rivers that are feeding into Death Valley. There's a lake. There's shorelines around that lake. And just to prove to you that Death Valley is quite dry, but just to prove to you that when it rains like crazy, in fact, people go kayaking out in the middle of Death Valley because that basin fills with water, right? In particularly wet years or wet springs, you'll get water filling that basin and you make a lake. So what happens is, for all of this whole area of southeastern California, all of these basins that are the result of the crust pulling apart, rifting, they fill with lakes. And Lake Manly is the lake in Death Valley. It's the end of the line. Water flows in there, and the only way it leaves is through evaporation. Okay? There's no outlet to that lake because it's the lowest spot, right? And so this is what could happen when you have a particularly wet spring. Now, have this image in your mind, And let's go back to this picture that the artist put together. And all of the pieces are there, right? The artist put in these mountains, that's just like the Black Mountains. The artist put in this lake, and notice there's lots of dinosaurs walking along the lake shore, right? There's the lake shore, right there. There's a river that would be feeding into this lake. There's the river coming in here at Death Valley. So this is what it looked like. And in the modern reference frame, the mountains on the side of our valley are today what we would call South Mountain. And the basin out here filled with the lake is today what we would call the Newark Basin, or I don't even know what the formal name is for the valley just south of us here of Coopersburg. Is anybody?
Indian Valley.
Maybe Indian Valley or the Percy, right? Percy watershed, right? Something like that. That's where we are today. So again, this is the way we try to use modern analogs to what perhaps the past landscape looked like. And this is a very good one. Let me see. Okay, so last thing here, then we'll take a break. These lakes, just like in Death Valley, you can get wet years and these lakes expand, and then you get dry years and they dry up. Okay? Well, that's driven by climate. Right? So we all know this. We have drought years and we have wet years. Over long geologic time spans, the climate is driven by ultimately the amount of radiation that we're getting from the sun. Over even longer time spans, it's driven by the amount of carbon dioxide that's in the atmosphere, right? To basically grow our greenhouse effect or take that greenhouse effect away. But independent of the greenhouse effect, the Earth and Sun are doing a dance as the Earth orbits the Sun, and over long periods of time, 20,000 years, 40,000 years, 100,000 years, the amount of energy that the Earth receives from the Sun varies. And that drives these broad climate patterns. These are things that we call Milankovitch cycles. They're named after the Serbian astronomer who discovered them. And what they predict is that over these long time spans, lakes in a rift valley should grow and then shrink back to small. Grow and shrink back to small. And it should do it following a very regular beat. And that's what's shown here. Here is a single cycle, and the way you read this is the thicker these black lines are right here, that means the lake is growing. And so when we go look at the rocks, including those rocks right on the rail trail, because when you're standing on the rail trail at eye level, you're looking at a deep lake deposit. Okay, so that is and you'll know you're looking at it because it's recessed into the outcrop. When you go, if anybody who's been there, you know what I'm talking about. There's like a layer, it looks like somebody like carved stuff out of it. That's the deep lake right there. Okay, and so there was a deep lake, and then that lake dried up. And you see this cycle, and we now know that that full cycle of growing to a big deep lake and then going away takes 20,000, 25,000 years. But then that is stacked together. There are these 20,000 year lake cycles that you'll see 1, 2, 3, 4, 5 of them. 5 times 20 is 100. That's a 100,000 year cycle. And then you'll see these 100,000 year cycles bundled 1, 2, 3, 4. That's 400,000 year cycles. Those are the exact Milankovitch cycles predicted by orbital dynamics. So these lakes are like tape recorders. Does everybody know what a tape recorder is? We don't have them anymore, but they're like tape recorders. They're tape recorders of Earth's climate. And globally, you guys, right here at Coopersburg, these things were first discovered here. Globally, here. This was some of the first evidence. The prediction of Milankovitch cycles started in 1914. The geologic proof that these things were real started right here in the 1960s. And I find that just amazing, that our backyard was so important scientifically for this. Yes?
So something occurred to me lately, a little bit different, additional to what you just described. So they say our our weather is also influenced by ocean currents.
Yes,
Ocean currents were colder when glaciers were melting.
correct.
So what creates glaciers sometimes is a super volcano, which throws all that stuff in the air, creates an ice age, or recently it was so great, you know, geologists is just great. They found that layer of magnetic stuff from an asteroid hit that they believe hit the glacier in Canada. But anyway, so maybe to save, you know, all this stuff about automobiles and all, maybe to save the world, the only thing that's going to happen is we're going to be extincted by an asteroid hit or a super volcano like Yellowstone.
And you know,
But
all
maybe
that
the
is
water,
possible.
maybe
I
the
hope
water,
it doesn't happen in my lifetime.
or
but
maybe
I'll-
all that melted ice puts so much water weight in the oceans that it forces the super volcano. What a concept that is, huh?
That teleconnection is yet to be tested. So
Well, there'll be no testing when that hits.
But there's actually several points well taken in what he just contributed, which is that these ice ages that we go in and out of, they're 100,000-year cycles. They're driven by these Milankovitch. At the very big picture, they're driven by sun insulation issues. So the ice sheets grow and decay on these 100,000-year cycles. Okay? So this imprint, this climatic sort of beat, our planet has a climate beat, and sediments can record that beat. And if we listen to it, we could hear it. And this is part of the first place where geologists learned how to do that. Okay? Which is really, really amazing. Okay, questions? We have a little bit about dinosaurs to talk about. This has been all about geology so far, right?
Before we get into dinosaurs, I live on Pass Road.
Yep.
Wawa,
Yep,
or east of us.
yep.
We live on the base of Lake Hill.
Okay, got it.
Mostly on the stones we dealt with farming or Flintstone.
That's right.
Bottom of the valley, north side of the other slope is all probably dye base. That's where the quarries.
That's exactly right.
40 years ago, and supposedly all these years, I was never in such close proximity to a geologist. I found this in my fashion. At first I thought meteorite, but no, it's no iron. Volcanic intrusion.
Yeah, I hate to burst your bubble.
Slag.
That's slag.
It's
It's from an iron furnace.
Wow. I mean, you weren't nowhere near the road or.
No, but people unfortunately move stuff around like crazy. That's
Well, it
slag.
still looks cool.
No, it is. It's very cool. So that is a human-made volcanic rock, a human-made igneous rock. It was made in an iron furnace.
Very good.
Yeah, would you agree that that's slag?
This has happened to me before too. Yeah.
Exactly.
Right.
Yes,
Slag.
But you mentioned Flint Hill. Okay, you know what Flint Hill? Where would Flint Hill be on this picture?
Well, it's the highest mountain in Lehigh County, I know that.
Today it is. Okay, on this picture, Flint Hill would be one of these alluvial fans. This thing right here.
Okay.
So Flint Hill is, like you said, made of a quartz. It is a quartz pebble conglomerate, and it is one of these alluvial fans. It would have been a fan of debris pouring out of those mountains, and the fact that it's the highest today means that quartz flint is harder and more resistant to erosion than the mountains that it came out of. Those mountains have been reduced by erosion, and the mountains are now lower than their old deposit. So on this picture, Flint Hill would be here. Up here would be one of these alluvial fans right there.
Is that real flint?
Flint is a colloquial term for bull quartz, and so yes, it's real flint. And whether or not you can make a flint walk out of it, or whether you can get a spark out of it, is I don't know. But it is flint is just.
Is it what we call I've never seen it. Is it what we call jasper?
Jasper's a little bit different. Have people been to the Veracruz Jasper site?
Yeah.
It's a little bit different. That is That is what we would
It's
call.
all around here, yeah.
It's chalcedony, so it's microcrystalline quartz that is the result of a hydrothermal process.
Yeah, where they built that hospital, that hospital building just down the road here, north of here. I was in that field before they bought it, built it, and the guy let me take all the flint I wanted out of it.
Excellent.
That was just chock full of flint, that construction site.
Other questions before we go to dinosaurs? Are we okay on time? Are people all right? Am I bringing something here? I know, I'm sorry, I'm talking long here.
Are you taking us to the inside scoop?
We're all going to the inside scoop. It's not my fault, you're asking good questions, it's your own fault. Let's talk about dinosaurs. This is what one of the dinosaurs would have looked like, walking on the lake shore, that ultimately would get covered by sediment and become our footprint site. Okay, how good are you guys at this? What do you call it? This is now, I thought that last time we had a bunch of youngsters that knew the names of all of them.
You're right.
Who's T-Rex up here? Where's T-Rex? This guy, that's T-Rex. Where's Stegosaurus? Stegosaurus. Where's Diplodocus? That's Diplodocus, okay? So let's get some names up here. And I just break them out this way. This is when dinosaurs first took over the world in the late Triassic. There's the main dinosaurs of the Jurassic period, and those are some of the big dinosaurs of the Cretaceous period. And in all three times, we had dinosaurs that were adapted to different kinds of lifestyles. So these, like, look at this guy right here. What would you, for this guy, and I'm going to tell you it's a carnivore, right? So it's a carnosaur, it's a meat eater. And that thing is, by the way, about as tall as you or me. Okay, it's only about as big as you or me. In today's world, give me an example of a mammal that would be agile, a really good hunter, something not much, as big as a human or maybe even smaller than a human. Like a wolf. Exactly. These were the wolves of their day. So they had a lifestyle, that they were successful. You know what wolves do to be successful. They kind of did the same thing. This guy over here, these are all herbivores. All right? In the Cretaceous, you had a herbivore that looks like this. Take away the frill here and just talk about the horns. What would be a big mammal herbivore with horns on its head? Rhinoceros. Those are the rhinos of their day. Right? So this is what biology does. Biology creates niches for animals and plants to be successful. And then the actual animal or plant that evolution creates could be a dinosaur or it could be a mammal, but the lifestyle is the same. Right? You're eating the same food. You have to have the same kind of protections. And you have to either be agile or not. So those things don't change through time. But the actual animals that are doing that do change. So these are some of the main, and the big ones, the biggest dinosaurs, the biggest land animals that ever existed are these sauropods. Right? So these things are just gigantic. You go to a museum, these things are 100 feet long and 40 feet tall. They're just gigantic animals. So for Coopersburg, a little bit more specific to Coopersburg, all dinosaurs, because Coopersburg dinosaurs are these Triassic dinosaurs, they're the early ones. Right? There's no big Diplodocuses or T-Rexes yet. All dinosaurs come from some sort of lizard-like animal, reptile that's called an archaeosauromorph. They existed prior to that extinction event in the Triassic boundary, at the late Permian boundary. And when that Permian mass extinction occurred, lots of other animals went extinct. And these survived, and they evolved into two lines. One that would become things that we call dinosaurs, and one would be things that called phytosaurs. They look like crocodiles. Right, so that's the way they went. Yes?
Well, when did they move from the water to the land?
That had already been done all the way back in the Devonian. So fish came out onto the land as amphibians, back all the way into Devonian. Yeah. Now for dinosaurs, when we think about skulls, and think about your own skull, I don't know how often you think about your skull, but think about your own skull. All mammals have skulls that look like this. They have an eye opening, they have a nose opening, and there's one more opening in the back of your skull. All of our skulls are what we call synapsid skulls. They have one more opening back here in the back. Okay? And dinosaurs had two openings. They're called diapsid skulls. So dinosaurs were reptiles that had these two skull openings, and that's one of the ways, like when you find these ancient animals, you say, is it a dinosaur or not? If they've got these two openings in the back of their skull, you know it's a dinosaur. Okay? And then there's other reptiles, like turtles, they don't have any opening in the back of their skull. So that's how you can tell base reptiles from diapsid reptiles, which are dinosaurs, from mammal-like reptiles that only have one opening. And so mammals came from a reptile. This would have been the ancestor of all mammals, right, because of the one opening in the back of the skull. And on a dinosaur tree, you know, here's the dinosaur tree, the so-called bird hip and lizard hip dinosaurs. The cool thing is that the tracks at Coopersburg contains examples of both. And the main ones would be, this would have been a plant-eating dinosaur called Atripus, and then a meat-eating dinosaur called Coelophysis. And both of those tracks are present at Coopersburg, and I have examples of both of them up here. Okay. This is what the Coelophysis track looks like, and like this one right here is a nice Coelophysis track. And then this is what Atripus track looks like. It's a little bit different because it has a little cleft right here. It has a little cleft in the back. And this one, this guy is a plant eater, and this guy is a meat eater. This guy was walking on 4 legs, and so you can see the front foot is right there, and that's the back foot. Coelophysis is only walking on 2 legs. It's bipedal, so you only see the 2 feet. So this is what the Coelophysis looked like. This is one artistic rendition. This is a complete other artistic rendition. This one is colorful, and it's about the size of a human. This one is colorful because this artist covered it with feathers. And we don't know if that's true or not. Okay, we do not know if that's true. We do know that it was some type of dinosaur like this, like a Coelophysis, that ultimately is the progenitor of all birds. So feathers are probably here, not for flight. What else do you use feathers for? For warmth, exactly. Thermal regulation. So feathers probably are a way for early dinosaurs to deal with colder temperatures. Or even today, when a chicken is born, are the chicken feathers the same as when they're old? No. So what are little chicks covered in? Down. Exactly. So and for thermal regulation reasons, right? Not just to make them look cute, right? There's for thermal regulation reasons.
Okay, here's another thing that's bothered me for years. You hear, oh, birds are a dinosaur. When did they switch from cold-blooded to warm-blooded?
There's good evidence that dinosaurs may have been warm-blooded.
Oh, really? Okay.
So
That's
this is really, no, that's right. This, in terms of thermal regulation, it's a really hot topic as to how you can just look at bones and figure out if you're warm or cold-blooded. Some of them probably were cold-blooded, others may have been warm-blooded. Just like today, there's a wide range of thermal regulation in mammals and fish and others, right? So that's what the coelophysis looks like on that painting that I was showing you. Okay? And they probably hunted in packs. In fact, we know this because there's some mass graves of these things in New Mexico at a place called Ghost Ranch, which is a really cool place to visit. And there's just dozens and dozens of these things that were killed catastrophically in a sandstorm. And so they probably hung around in packs, just like wolves do today. Afterwards, they became very big and scary. And so in the Jurassic and Cretaceous, they become the velociraptors, which everybody likes to, they're the villain, right, in Jurassic Park. But also here at Coopersburg were these guys. So this is now a herbivore, and it's walking on 4 feet. This is Atriopus. And we see at Coopersburg the front feet and the back feet. And this is an early herbivore dinosaur that's going to ultimately, by the time we get to the Jurassic and Cretaceous, become those giant sauropods. So things like brontosaurs and diplodocus. But here, those had not been, they weren't around yet. This is what was around at Coopersburg time. And so there's the artistic rendition of them, and here's some examples of what they evolved into. These are some of the duck-billed dinosaurs at the American Museum of Natural History. So yeah, to end the talk, we already mentioned this, the dinosaurs benefited greatly from the mass extinction at the end of the Permian, but then at the end of the Cretaceous, there was one very bad day. This was a very bad day. A 10-kilometer wide asteroid, estimated, hit the Earth at very high velocity. It hit the Earth at a place in what is now today the Yucatan Peninsula of Mexico, basically at about Cancun, Mexico. And at that time, that was shallow ocean. And it didn't hit the Earth straight on. It hit it at a little bit at an angle. And that angle was actually pointed towards North America. And the explosion was obviously enormous, but there was a gigantic tidal wave, many hundreds of meters tall, that washed across North America. There was a giant air blast that ignited forest everywhere, and they burned. And it extinguished life everywhere in its path. And then if you happen to be on the other side of the Earth, you didn't feel the direct effects of this, but this put so much dust into the atmosphere that it cut out photosynthesis for several years. And you just had a global winter for several years. And the dinosaurs did not make it through this. And you think about the animals that did, like a turtle made it through this, and an alligator made it through, but the dinosaurs didn't. What do turtles and alligators do in the winter? Yeah, they burrow in the mud and they wait it out, right? So the animals that can do that made it through. If things are bad here for a bird, what could they do? Fly away, right? The birds made it through this because they can move and get away from the worst of it. The dinosaurs didn't. The ecosystem collapsed enough that the dinosaurs did not survive this. But, like I said, birds were mobile enough, evidently, to survive this, and you started out with things that looked like coelophysis, the same thing that was walking across here at Coopersburg, and the feathers that probably existed initially for thermal regulation were adapted for flight. And birds then were able to do what birds do. Birds are wildly successful, as you know. Right? That's the end of my talk. I really appreciate your attention, and I'm happy to take questions, and we can look at the fossils. Question?
Hypothetical question. Read about it every once in a while. I don't know whether it's true or not, and they claim it could be DNA from some prehistoric animals. For example, a mollusk, or a mastodon.
Yeah.
Or something that has some substantial DNA
Yeah.
that could be worked with.
Yeah.
Is that a viable option, do you think?
So there's an actual company out there that devoted to bringing back extinct animals this way.
How successful have they been?
Not successful yet.
Not yet.
And so the argument, the question is about, can you resurrect old DNA to actually take an extinct animal and reconstruct it? And one of the big candidates for this are mastodons and mammoths, which, by the way, because you brought it up, I brought some mastodon teeth for you here and some mammoth teeth if you want to look at that up here. The reason why is because when these things die, particularly in the far north of Siberia or Alaska, they get encased in ice and they're spectacularly well preserved, like amazingly well preserved. And the argument is that you'd be able to take the DNA out and you'd be able to implant it into the egg of an African elephant, and you'd be able to have an African elephant be a surrogate and produce a mammoth again. They've not been successful doing that. The DNA tends to be too degraded. Like it's you know that you can code enough of it to say, yes, this is something different than any animal that's living right now, but it's not viable enough, it's not intact enough to actually successfully reproduce. But there is a company out there that is dedicated to doing this. It's amazing what venture capital can do. Yes.
How do you feel about the dire wolves? Are they really dire wolves? Was
That's right.
Sufficient change?
Same arguments. Same arguments as to whether dire wolves are really extinct or whether in fact they just represent the forms that are here now.
A company claimed to have brought back dire wolves recently.
That I was not aware of, so yeah.
I'll show you the article later.
Yes.
Well, these stones, where did they come from?
These come from different places. These come from Connecticut. These come from, I don't know the exact provenance of these. These are mammoths and mastodons. I'm guessing probably from bogs here somewhere in the East Coast where these fossils have been found. Recently, amazingly so, within about the past year, a student at Franklin and Marshall College was walking in a stream in Lancaster County and picked one of these up and didn't know what it was, and they like threw it like a rock, and the professor's like, bring that back over. And it happened to actually be a mammoth tooth, right? So you find these things
Can I ask
occasionally.
you, were these found around this area?
Everything that's here, everything that's in the middle right here, these are from the Coopersburg Dinosaur site
Okay.
itself.
Because I lived just in Center Valley, and I lived on a farm,
Uh-huh.
and I'm no spring chicken, but I never seen anything like this.
Depends on where your farm was. You could have been on these kinds of rocks, or you could have been on rocks of the Saucon Valley. Would have been different. But if you tell me where your property was, I can tell you what kind of
Just a
rocks
few
you're on.
miles over.
Over what direction are we going?
Like these hills, the university.
By DeSales. Well, you would have been. Well, you were probably on rocks of the Saucon Valley. You probably are not actually on these rocks. You
Okay.
might have been on a limestone,
You
or.
know, living on a farm, and we had a lot of acres, and I haven't seen that, but it's,
What is that little hill? What's the little hill called by DeSales? It has a name. It's a little.
Flint.
Okay, so Flint Hill is that one, but there's also that little hill right by Landis Mill Road. You know what hill I'm talking about? It has a name, I can't remember it. That's granite, and so you would never find any of this stuff if you were on that little hill.
Well, they used to mine iron.
Yeah.
Over, right on the farm where I was raised.
Exactly,
Yeah.
exactly.
So,
Yeah, that's different than those rocks.
yeah.
You've got a good eye. You have a very good eye. Other questions? Yes?
I'm just curious about what would be the geology, or would we find anything over on Beverly Hill?
Okay, tell me where Beverly Hill is.
Over the big hill going into Lineport, down into Lineport?
Oh, right, yeah, okay, so I've been out there, yeah, and Beverly Hill. Do we have internet here? I can tell you in a second. No, okay, so I can tell you in a moment.
Oh,
Hang on.
okay.
Other questions while I'm looking this up? Because I have to cheat and go to the map.
What app are you using?
I'm using Rock.
Yeah, that's a great app.
Look it up and see if you get to it first.
Where are we looking for?
Beverly Hill.
Everybody knows where.
But that's just west of us, right?
Right, and because the Jasper stuff is not that far.
Right. keep going with questions as we look this up. Other questions?
Got a bird up there, a colorful bird. I don't know, that's supposed to be the Areopteryx.
That's what it is. That's Archaeopteryx.
Is that a true
Oh, yes.
flight
Yeah,
bird?
best people can tell yes, because this has gone back and
So
forth.
much dissension on
And
that.
it's gone back and forth, but people, the most recent would say that yes, that the physics of that wing would allow it to fly.
What would be its range?
Don't know.
Short,
Don't know. Yeah,
but that is a true flight bird.
yes. Because one of the questions that was coming up is that bird even capable of flying? Because what else do you use, if you don't use feathers to keep you warm, what else do you use feathers for? And if you don't, if they don't help you fly, what else could you use them for?
We have birds that have feathers, but they don't fly.
If you don't use the feather to keep you warm, and you don't use the feather for flight, you could use it for something else. What could you use it for? Mating. What do peacocks use them for? Right? Right? Attraction. Right?
I cheated, I had her find it.
Oh, so you're on the nice. You're on the lowest part of the column. No fossils. Sorry. Thank you. Thank you. Other questions or comments? So it's really been my pleasure. Thank you. And again, come on up and look at the fossils and look at, if you have any questions on the stuff that's on the table, I'm happy to answer any of those questions. Don't be. That is fossilized tree bark.